So we're looking at some hypothesis testing a little bit more here today. Um, so yesterday's video was about the tires, okay? And the focus was that you wanted to state your null hypothesis, all right? And then you wanted to collect some data, perform a test, and decide whether or not your hypothesis was supported. And then in the end, you kind of make a little statement that tells you whether or not it was or was not. All right. So we're going to do that again here. A little extra bonus question here. So let's read this one. So this is historically 20% of pigs who contract the swine flu, they die, unfortunately, from this disease. Now, we've got a company here that's tested out a new cure on 250 of these pigs. Of the 250 pigs, 215 were recovered. Make a hypothesis test for the cure's effectiveness with a significance level of alpha equals 1%. Okay. And so that's basically what we're looking at here. All right. Oop, let me erase that. Sorry about that. All right. So we're looking at all of that stuff. So essentially, can this study be modeled with a normal distribution? We got to set up a hypothesis test. We've got to conduct a hypothesis test with a significance level of 1. And can the company claim that the new drug is effective, right? So these are various questions that can be answered here. First of all, this first question is, can this study be modeled with a normal distribution? First of all, we have to realize that this is a binomial distribution, okay? This is a binomial distribution. And remember, there was a stipulation that said if P times N or if Q times N were either one of them were less than 5, actually. So basically, it says that this must be greater than 5, and this must be also greater than 5 in order for all of this to work out. Okay. Well, let's basically figure out, well, what is N? Okay. N happens to be 250, right? Because that's the number of things in the sort of sample, right? The number of people we've asked, in a way, okay? Or the number of items tested, in a way. These are pigs, though. And then P happens to be 20%, okay? And Q happens to be 80%, all right? Or 0.8. And I guess I should write 0.2 over here for 20%. So 0.2. Question is, what's P times N and what's Q times N? Well, P times N is 250 times 0.2. All right. And so that's around, I guess, is that 50? I think it is. Let's just double check that. It's pretty late over here. So it's 250 times 0.2. It is 50. All right. So that's greater than 5. And the other one is 200. That's also greater than 5. And so these guys are pretty good to go. All right. So that was basically this question is, can this study be modeled with a normal distribution? And the answer is yes, because P times N and Q times N are both greater than 5. Okay. So now we have to set up a hypothesis for the cure's effectiveness. All right. That should say test, by the way, a hypothesis test. I'll change that on the next go around here. So basically, what we want to do when we do a hypothesis test is we want to state a null hypothesis and a alternate hypothesis. So in this case, this one's tricky. I'm going to state a null hypothesis, which is, it's going to actually have a train of ideas. Let's hear. So the null hypothesis is that the cure was not effective. Okay, and I'll explain why that's the case. And the alternate hypothesis is that the cure was effective. Okay, why would I write it like this? All right, so the cure was not effective. It actually means that if the cure was not effective, then basically our data would support that 20% of the pigs survived, right? So basically, that would mean that 20% of the pigs survived, right? If the cure was effective, then the other thing what happens is more than 20% of the pigs survived. Okay? Does that make sense? So normally, let's go back and look at our scenario here. Normally, 20% of the pigs survive, right? So that's what we're looking at. Normally, 20% of the pigs survive. If we now give them a test for this drug, and all of a sudden more than 20% of the pigs survive, then we can conclude that this drug or this medicine or whatever it is was effective. Okay, well, so that's the way that we're looking at this. Okay, but now let's go ahead and set up an actual hypothesis test and see, and we're going to compare this with the 1% here. All right. So I'm going to go ahead and conduct the hypothesis test. That's what we're now doing. This question here, conduct the hypothesis test. So this is section U. I don't know why it's just labeled U, but that's what it is. And so here we go. We're conducting the hypothesis test. So in order to do that, I need an X, right? Oops. Let me get just a marker here. I need an X minus the average over the standard deviation, right? That's going to be my z-score, all right? Now, X in this case is going to be 215. The average is going to be P times N, or 200. And the standard deviation is going to be the square root of P times Q times N, okay? And that one I'm going to have to calculate. So let me pause that and I'll get a calculation on that. All right, so I got that. It's a 6.32 is my standard deviation. My average is P times N, and my X value is 215, okay? So basically what I'm going to do is I'm going to run through this hypothesis test. Let me just write down what I'm going to write here. I'll erase my formula here and I'll just kind of start fresh. So basically what I want to do is figure out the probability that you would get 215 or more pigs, okay? Because, and what I'm going to do is if I want 215 or more, I need 214.5 minus 200 over a standard deviation of 6.32. All right. And what I'm going to do is I'm going to pause it again. So I got a 2.29 here for the standard deviation. For the z-score. Okay. And so there we go. A 2.29 is over here. It's a 98.9%. Okay. So I ended up with a 98.9%. Oh, but wait, we are doing or more. And so this is not the correct percentage because we have to do the complementary percentage, which would be 1.1%. Okay. And now what we do is this is P. It's oftentimes called P, little p, even though that actually is called P up here. So I probably won't call it a P there. So we'll just call it the final percentage. We have to compare that with alpha. Is this little percentage here greater than alpha, or is it less than alpha? So as we can see, 1.1% is greater than alpha, or 1%. Okay. And so therefore we conclude, let's go back up to there. What do we conclude? If our final percentage is greater than alpha, then the original hypothesis is true, which is the cure was not effective. So therefore, HO is supported, or the cure was not effective. Okay. So now you might be thinking to yourself, what the heck? How did that happen? So let's take a look at this. Now, I'm going to go ahead and have to draw our eyes in on a few different things here, okay? So, what does this 1.1% actually signify, right? This 1.1%. I keep erasing things here. This 1.1% signifies that, let's say, all right, where does this 1.1% come from? Let's go back to here, okay? I've got a 98, right? This is that's where the 1.1 comes from. It comes from this formula here, this 214 minus 200 over 6.32, okay? Let's take a look at this formula here. This formula basically is saying, what is the probability, okay, of getting 215 or more out of, if the average is 200, given the fact that the standard deviation is 6.32, okay? Given that the standard deviation is 6.32. And so as a result, we get a 1.1% here. So basically, what this 1.1% means, it's like, let me write this down. There was, right, a 1.1% chance, okay, of, well, that's supposed to be a C, chance, getting 215 or more pigs to survive if they had a 20% 80% chance of survival. Okay. So there was a 1.1% chance of getting 215 pigs or more to survive if they had a 80% chance of survival. Okay, so you might say, okay, well, that was a reason. That seems like a pretty low percent, right? But we did choose an alpha of 1%. Okay. what does that end up meaning? Basically, what that means is we're saying to ourselves that there was a reasonably high chance that we would have gotten this number of pigs to survive, 215, even if we hadn't, even if they all had a 20% chance of survival. So basically, what we're saying is that 20% chance of survival is um, 80% chance of survival is it's in play. It's legitimate. It's what happened. Okay. And so therefore the cure did not change the 80% chance of survival. Okay. The cure itself did not change the 80% chance of survival. Oh, and by the way, I actually messed up back here. I'm looking at it now. This right here was supposed to be 80% because I wrote 20% die, and this was supposed to be an 80 here. And this one as well. Okay. But it's still the same concept, all right? Anyway, so that's basically the whole flow of that one, all right? Okay, I want to point out a couple of things where students are going to end up having just some possible issues here. Okay, Oop, let me erase that. So notice in this area here, I wrote P as 0.2 and Q as 0.8. But then in practice, I actually used the opposite value. If you look at this over here, I actually placed 80% right there. So you're saying Q is 80%, right? Why is that the case? Well, because my X value, remember my X value way back here, it talks about pigs who survived, all right? So therefore, my point of interest in my formula down here needs to have pigs that survive. I need to compare the expected number of survived pigs with the actual number of survived pigs. Okay. In order to do that, I need to make sure I had to switch my P's and my Q's. All right. And so mind your P's and your Q's here. I don't know if you guys have ever heard of that. My dad used to say that all the time. Now I know why. Whatever the case, I had to switch my P's with the Q there. And so basically that's one way where students might mess up. They might end up using 20% here, in which case you would get a 50, okay, instead of a 200. But then you would place a 50 here, but then you would get this really wild z-score, okay, which, okay, maybe you can get a wild z-score, but maybe you don't want to get a wild z-score either, okay? So you just got to make sure that these two numbers jive, okay? Another area where students could mess a question up like this is why did I decide to do 215 or more rather than 215 or less? Let's go back to the chart, okay? So basically, we were expecting 200 pigs. We got 215, all right? And so I want to figure out, oh, that's not going to work out for us. Here we go. let's go ahead and boom. All right, there we go. Shoot. All right, always draw the curve first and the numbers later. That's I've learned that. Okay, so here's the what we were expecting. We were expecting 200 pigs to survive, but in reality, 215. 215 survived. And so as a result, what we're doing is we're looking for what's this slim chance over here that we got. Okay, so I wanted to figure out this smaller probability of 215 or more. Okay, I don't want to figure out what's the probability of 215 or less. I don't want to include what I was expecting to happen in my search. I want to sort of search for the improbable. Is this, because basically what we're doing is we're making a hypothesis test improbable. Okay, we're making a hypothesis test here, trying to determine if this cure made some sort of miraculous number of pigs survive. Okay, well, how would we know if a miraculous number of pigs survived? If the survival rate gets pushed way out here, for example, let's say like 222 pigs survived. Well, that number is way out here. Then all of a sudden, we're getting a really slim probability of 222 pigs or more, which basically, why would we get such a slim probability to occur? If that happened, we would start to conclude that the cure or the drug or the vaccine or whatever they gave these pigs was the thing that caused this survival rate to push itself all the way up to 222. Okay, that's if we got 222. But in reality, we only got 215 pigs to survive. And so basically what we're concluding here is that this is not pushed far enough. This 215 is not pushed far enough above what the expected survival rate would be in order for us to conclude that this cure is effective enough. Okay, in order for this cure to be effective enough, it would have needed to cause a significantly greater number of pigs to survive. Okay, and that's kind of going back to our ultimate sort of conclusion here, is that this 1.1% chance just isn't small enough to make us, to convince us that we that we need that this cure is effective. Okay, and I just want to mention one last thing here. All right, why are we choosing a 1% significance level in a scenario where you are talking about implementing a sort of medication or vaccine into the market? You want to have a very low significance level. Why do we want a low significance level? Because we want to basically say, look, this, in order for this drug or this vaccine or this cure to get released into the market, it must have saved or it must be a miracle. It must be this drug that creates miracles. It saves lives, right? Because once a drug is implemented into the market, it's difficult to get it recalled or taken away, right? And so in order for something to be admitted into the market, it must be extremely effective. In order for it to be extremely effective, it needs to pass a 1% significance test. And a 1% significance test means that it needs to push what should have happened. Or, what should have happened was 200 pigs survived. And in order for us to claim that this drug was effective, we needed a bigger push of something like 222 or 230 or something pigs to have survived. And if that were the case, we could say, yes, this drug was a miracle because there's no way that those number of pigs could have survived without this some sort of cure, and so therefore the cure must have been effective. Okay, and so that's kind of how this hypothesis test plays out. There's a lot of innuendos and different little ways that you got to tweak your thinking in order to get around this question. This is a highly challenging question, and always kind of deserves a little bit of extra attention. Okay, there you go. That's a hypothesis test.